Good afternoon, students. Let us start the fourth hour class now. You will have to bear with me for the previous hour class also and for the present hour class also. Why I am telling you is, these are all some fundamental concepts where sometimes I will go at length about discussing all these things. At times you may feel it boring also, or you may feel as if why this much of explanation is required. But as I told you, it is very important to understand all these concepts. Otherwise, in future we have lengthy mathematical derivations and mathematical results. If these basics are not understood properly, later on nothing will be understood as such in this particular module. That is why I will have to go in slightly larger details. Fine. As I have been telling in the previous class, the probability of error is a joint probability as well as a transition probability together, where we transmit 0 and we get 1, and we transmit 1 we get 0. So naturally 1 minus PE is the average probability of correct reception. Let me proceed further with this binary symmetric channel. Binary symmetric channel means that P11 equals P00. That is called as binary symmetric channel. Now let me proceed in this manner. The modern communication channels are now carrying an alphabet of more than 2 symbols. I have been giving you the examples of ASK, FSK, QPSK. Now ASK and FSK have 2 waveforms. QPSK has 4 waveforms. 8PSK has 8 waveforms, and so on. Let me simply try to annotate and show you the waveforms for ASK. Now ASK will be like this, one waveform like this, one waveform like this. That means absence of carrier is 0, presence of carrier is 1. Now this can be ASK. FSK can be like this. This is one lower frequency and this is one higher frequency. I am not able to accurately write it, but you can see, of course, in the upper diagram slightly it is got offbeat, but you can assume that the upper frequency is a lower one and lower frequency is a upper one, higher one. Means, now in ASK this can be 0, this can be 1. In FSK this can be 0, this can be 1. For detecting ASK it is very easy. Detect wherever a waveform is present, that is 1. If no waveform is there, it is 0. For detecting FSK now this is ASK, this is FSK. Now this is ASK. This is ASK and this is FSK. Now in case of FSK, you have a lower frequency and a higher frequency. So here you will have to use 2 types of filters, 2 types of band pass filters, where you will receive this frequency separately, this frequency separately. FSK is used extensively, it was used extensively in fax machines, it was also used in radio paging systems, and one variation of FSK called GMSK was used in 2G mobile phones. Gradually this FSK become obsolete as well. ASK is right now used with all Bluetooth and Zigbee communications. ASK will remain, FSK also may remain in some newer applications in future. Now you can see ASK has got 2 waveforms, FSK has got 2 waveforms. You may say that in ASK there is no waveform here at all, but that absence of waveform is also a waveform because it is a symbol there as far as our communication system is concerned. Now in QPSK you can have 4 waveforms. I will try to write it here. In QPSK you can have one waveform like this. Now this is a complete waveform, right? This is a complete waveform. You can have only this waveform like this, only with the 90 degree, and then you can have only this waveform like this. From here it will start this way. Then you can have one more waveform like this. You can have one more waveform like this. That means you can divide this 360 degree cycle into 4 each, and 90 degree one waveform, another 90 degree one waveform, another 90 degree one more waveform, another 90 degree one more waveform. That means 4 waveforms. You may seem as if all these are identical. No, I can write it in a different way now. First waveform like this, then that waveform like this, then next waveform like this, then next waveform like this. See, even though here I have written all those waveforms in the same fashion, they will have 90-degree phase shift. Now when they have 90-degree phase shift, actually it can extend up to one complete cycle. Let me try to write it further in a different fashion, where you can have one waveform like this. Imagine this way. Now you can have one more waveform like this. Okay, this is one waveform, 90-degree phase shift. Now you can have one more waveform like this. Okay, then you can have one more waveform like this. Now this is a complete one cycle, 360-degree cycle with the 90-degree phase shift one, with one more 90-degree phase shift. You can see that the first one and the third one will have 180-degree phase shift. And then the fourth one again with the 90-degree phase shift with the previous one. This way we can have 4 waveforms. Now when we have 4 waveforms, this can be used for transmitting 0, 0. This can be for 0, 1. This can be for 1, 0. And this can be for 1, 1. In this manner, we are transmitting a single waveform, but actually we are conveying 2 bits of information. This is called quadrature phase shift keying, where it will have 4 waveforms. Now you understand the beauty or the ingenuity of the technology now, where we have distinct waveforms and each waveform can contain within it 2 bits. Actually it does not contain 2 bits. At the receiver it has to identify this waveform and it has to again generate these 2 bits. That is how I have been telling you again and again that we are conveying more and we are transmitting less. Now QPSK can have 4 waveforms. Similarly 8 PSK, 8 phase shift keying, it is also called as OQPSK. That can be having 8 waveforms, each with the 45-degree phase shift. Now hence a channel which carries one of m possible symbols. Now there can be 2 symbols, there can be 4 symbols, there can be 8 symbols. Similarly, when we go for a latest method of modulation called quadrature amplitude modulation, in which it is a combination of AM as well as PSK. That means amplitude modulation along with the phase shift keying. Such hybrid waveform is called quadrature amplitude modulation. And in case of QAM, sometimes we abbreviate it and we simply pronounce it as COM. Instead of telling QAM, we can simply say COM. In case of this QAM or COM, we can have 16-point COM, we can have 32-point COM, we can have 64-point COM, we can have 128-point COM, we can have a 256-point COM. That way it can go on. Because it's a combination of different amplitudes with different phases. That way there can be m possible symbols. The number of symbols can increase now, depending upon the modulation technique that is used. Hence, a channel which carries one of m possible symbols is called a discrete m-ary channel, where m is greater than 2. It is called as m-ary channel. If it is only 2, then it is called as a binary channel. Now, if it is 4, it can be quaternary channel. That way it can go on. So, that is why here it is told m is greater than 2. If it is m is equal to 2, we don't call it as a m-ary channel. We call it as a binary channel itself. So, below shown is the probability diagram of a channel carrying 4 symbols or a quaternary channel. You can see this. I gave an example of QPSK, where a waveform will contain either 0, 0, if it is 90-degree phase shifted 0, 1, 180-degree phase shifted 1, 0, 270-degree phase shifted 1, 1. So, at input I can have 0, 0, 0, 1, 1, 0, 1, 1. Now, at the output, again 0, 0 can be received, 0, 1 can be received, 1, 0 can be received, 1, 1 can be received. This is what we presume. Exactly, we presume that exactly we will have only 90-degree shifted waveforms. Otherwise, because of the channel characteristics, there can be strange waveforms being decoded at the receiver also, because there can be waveforms which are not following this particular pattern because of the channel characteristics. Apart from this 90-degree phase shift, there can be strange phase shifts occurring in the channel as well. But now in this particular analysis, we are not considering all that. We are only considering that we transmit 0, 0, we receive 0, 0. Now, when we transmit 0, 0, there is a chance that we will get 0, 1 also, 1, 0 also, 1, 1 also. Similarly, when we transmit 0, 1, there is a chance that we will get 0, 0 also, 0, 1 also, 1, 0 also, 1, 1 also. Now, for each symbol being transmitted or each waveform being transmitted, there are 4 chances at the output. This is now a quaternary channel, where the issues are now much larger. You can see that we can name these probabilities now. Now, when x1 is being transmitted or when 0, 0 waveform is being transmitted, there can be 4 probabilities occurring in the channel. We may receive y1, we may receive y2, we may receive y3, we may receive y4. What we want is, we want to receive y1 itself, but we may receive y2, y3, y4. So naturally we will have p11, p12, p13, p14 are the probabilities. Similarly, for each one we will have 4 probabilities, and totally we have 16 probabilities. This is what I have been telling you in the previous class, that we are going to consider mainly the binary channel only, because it will be very difficult for us to compute the probabilities or errors, probability errors for the channels which are having more than 2 symbols, because it is going to complicate our mathematical work. Anyway, now we have software tools such as MATLAB, we have software languages such as C and C++, where now we can easily write programs for any MRE channel as such, and they can compute all these beautifully on their own. That is how we have automated all our communication models now using these softwares. Now, for our theoretical discussion, we are going to limit it to binary channel itself. Now we can understand the complication. We are having 4 symbols at the transmitter, we will be receiving 4 symbols at the receiver, but we will have totally 16 probabilities, and there will be a relationship between each one of them now, and that will become complicated now. When x1 is transmitted, only one of 4 output symbols has to be received. From the figure we have P of y1 slash x1 plus P of y2 slash x1 plus P of y3 slash x1 plus P of y4 slash x1 equals 1. Which means what? When we transmit x1, we will either get y1, y2, y3, y4. So the probability of all these y1, y2, y3, y4 being received is equivalent to unity. Please understand this. When we transmit this particular symbol x1, we have to get one of these 4 only, because these are the well-defined inputs and outputs. So probability of y1 and y2 and y3 and y4 together, when they are added, it is equivalent to unity. But y1 can occur when x1 is transmitted, y2 also can occur when x1 is transmitted, similarly y3 and y4. That is why probability of y1 being received in condition to x1 plus probability of y2 being received in condition to x1, similarly with y3 and y4, is equivalent to 1. So we can write that summation of j equals 1 to 4 with the probability of yj slash x1 equals 1. We can write it this way. We can write in the same fashion for other symbols as well. Okay. Please understand all these things thoroughly. Now we can write a channel matrix in terms of the transition probabilities. This is called as a channel matrix. We had written some matrices earlier for our Markov models using the tree diagram also. We had worked out some examples. Now this is similar to that, where we can write probability of y in condition with x. Means we will have to get 4 symbols at the receiver, provided we are transmitting 4 symbols at the transmitter. We can write this channel matrix now. P of y1 slash x1, P of y2 slash x1, P of y3 slash x1, P of y4 slash x1. First row corresponds to x1 being transmitted. Similarly, for x2 being transmitted, x3 being transmitted, x4 being transmitted. Please remember, the sum of each row is unity. Remember that we are getting y1, y2, y3, y4, one of them when x1 is being transmitted. So the sum of all the probabilities in each row of this channel matrix is unity. That is one of the properties of this channel matrix. Let me round off this word channel matrix. This is important for us. This is not an ordinary matrix now. This is called as a channel matrix. Unlike the other matrices, what happens is this plus, this plus, this plus equals 1. You will have to remember that. In the same way, for the lower row, the sum of all the row elements equals 1. Same is holding good for the third row and the fourth row. And this is one of the basic properties of the channel matrix, which is applicable to only the communication channels. Okay. Let me go ahead. Each row of this channel matrix corresponds to a fixed channel input, that is x1, whereas each column corresponds to a fixed channel output. Now that is the beauty of this. Each column, look at this, each column, let me annotate this once again. Each column corresponds to V getting y1. Okay. Probability of y1 in condition to x1, and that in condition to x2, that in condition to x3, and that in condition to x4, we are going to get the probability y1. So each row corresponds to a transmitted symbol, and each column corresponds to a received symbol. That is the speciality or property of this channel matrix. So now, each row of this channel matrix corresponds to a fixed channel input, whereas each column corresponds to a fixed channel output. The fundamental property of this matrix is that the sum of the elements along any row is always equal to 1, as I have told you already. This is because an input symbol should produce any one of the output symbols. The reverse need not be true. An input symbol should produce any one of the output symbols. The reverse need not be true. What does it mean? An output symbol can be produced due to noise as well. You can receive y1 as noise as well. I told you an example earlier about the in-band noise. Let us say in the GSM system between 890 to 960 megahertz, a symbol is transmitted. Now, if the channel produces the same frequency as noise due to some other information source or due to some other interference, now when that frequency is not transmitted also, you will be able to receive this particular frequency. That is actually a noise only. So the reverse need not be true. An output symbol can be produced due to noise as well. Hence, the sum of the column elements need not be equal to 1. Please remember that. Let me admit the student who is waiting in the lobby. Okay. Please remember, in the channel matrix, only the sum of the rows is equal to unity. The sum of the column elements should not be taken as unity. Otherwise, you may think here that as y1 is received when x1, or y1, y2, y3, y4 are received when x1 is transmitted, similarly y1 can be received by means of x1, x2, x3, x4 also. No, not necessarily. Without x1, x2, x3, x4 being transmitted also, you will still receive y1 because the channel may induce a noise that is y1. Okay. You can see so many such Tamil movies or Hindi movies where twin brothers will go one instead of the other. And there can be confusion with the audience also. There can be confusion with the people who are receiving them also, that they are receiving the original symbol. It may be a different symbol now. Okay. So that way, the sum of columns is not going to be equal to 1. Whereas the sum of rows is also always going to be 1. That is the one fundamental property of the channel matrix. So the reverse need not be true. That is, an output symbol can be produced due to noise as well. Hence, the sum of column elements need not be equal to 1. So in general, we can write a square matrix. In general, let us say 4 symbols are transmitted, 4 symbols are received. 8 symbols are transmitted, 8 symbols are received. That is how we define a discrete communication channel as well as a discrete information source, right? We are not discussing the analog sources, we are discussing the discrete and digital sources. So in general, we will always have a square matrix only. So for a square matrix, we can write that summation of j equals 1 to m. We are discussing about an emery channel where probability of yj in condition with xi is equal to 1 for all I. Whereas summation of I equals 1 to m of probability of yj in condition with xi need not be equal to 1 when for all I. Look at this. We are using these two parameters here, j and I. For j, yj condition with xi is equal to 1. But when I equals 1 to m, for yj in condition with xi, it need not be equal to 1. That means yj can be obtained even when xi is not transmitted. But yj will be obtained always when xi is being transmitted. When something is transmitted, definitely something is going to be received. That is for sure. But it is possible that when something is not transmitted also, something else can be received. That is what is the meaning of the lower line. A small note. Now as far as the input is concerned, we can write summation of I equals 1 to m of p of xi is always equal to 1. What does it mean? We are going to transmit either x1 or x2 or x3 or x4. So the summation of p of x1 plus p of x2 plus p of x3 plus p of x4 is also going to be unity. Remember this. Anyhow, this is obvious as such because from the information source, we are going to transmit any of these 4 only. For example, when you type a message, let us say you are typing an English message, the probability of A till probability of Z when they are added, it is going to be equal to 1 only, right? You are going to type your message, let us say I specifically told text message. Otherwise, you may put smileys, you may put a thumbs up, you may put many symbols. That is all up to you. Up to me also to some extent. But otherwise, let us say we type only a text message. Then A till Z, we are going to type only from A till Z. Then P of A plus P of B plus P of C plus P of D, like that goes on till P of Z is equivalent to unity itself. That is anyhow obvious. Now, using the theorem of total probability, I had asked you to revise your knowledge of statistics. You have already studied this theorem of total probability when you studied probability and statistics in the maths courses. Now you will have to revise that knowledge. If you don't recall that, again you will have to study it back and you will have to recall. I cannot teach you the theorem of total probability here now. Okay? We will be using the theorem of total probability in our course called Information Theory and Coding. I cannot revise all those maths basics which you have already studied earlier. That is the reason in the first year and second year you had studied 4 maths courses. Engineering is nothing but the usage of mathematics along with material science. Nothing else. Without mathematics, there is no engineering at all. There is no technology at all. That is for sure. Especially with electronics and communications, without the mathematical content, we cannot understand the electronics and communication courses at all. For that matter, for electronics and communication engineers, the knowledge of basic engineering mathematics is very much essential. Okay, so please revise the theorem of total probability if you have forgotten it. I am stating it briefly here. That is, probability of y1 is probability of y1 in condition to x1 into probability of x1. Because we are going to transmit only x1, x2, x3, x4. Now, me receiving y1 at the receiver, I can receive y1 when x1 is transmitted and y1 is received, provided x1 itself is related to this conditional probability. Similarly, me receiving y1 when x2 is transmitted, at the same time there is a probability of x2 being transmitted, because p of x1 into p of x2 into p of x3 into p of x4 is equivalent to 1. So this is what is called as the theorem of total probability. It is a product of individual probability and the conditional probability, and it is the summation of all these products. There is statistical dependency also, then it is multiplied. There is statistical independency also, then it is added. Now, probability of y1 equals probability of y1 in condition of x1 into probability of x1 plus probability of y1 in condition to x2 into probability of x2 plus probability of y1 in condition to x3 into probability of x3 plus probability of y1 in condition to x4 into probability of x4. This is the theorem of total probability. Based on this theorem, later on we have one more theorem called Bayes theorem. That theorem also you have studied in the maths courses. You will have to revise that also. We are going to make use of the Bayes theorem in this particular chapter extensively. Now, knowing the input probability P of x1, knowing the input probability P of x1, output conditional probability P of y1 slash x1, and the output probability P of y1. Look at this. We know the probability of x1. We will know the conditional probability of obtaining y1 when x1 is transmitted. And we will know the probability of y1 at the output. Okay. Now, this is output probability. This is input probability. This is conditional probability. Remember this. P of x1, x2, x3, x4, they are input probabilities. P of y1, y2, y3, y4 are output probabilities, and P of y1 slash x1 till y4 slash x4, which I had shown you in the channel matrix, all those 16 are conditional probabilities. Now, knowing these things, we can obtain the input conditional probability using Bayes theorem. That will be interesting now. Knowing the input probability P of x1 and output conditional probability P of y1 slash x1 and the output probability P of y1, the input conditional probability can be found using Bayes theorem. Now, P of x1 in condition to y1 is equivalent to P of y1 in condition to x1 into P of x1 into P of y1. Now, this is important. Let me highlight it. Okay. Now, look at this. You may seem this is strange, but I will explain. Probability of x1 in condition to y1 is obtained here. Now, you may think, how can input be in condition to output? y1 is the symbol that is received at the destination. x1 is the symbol that is transmitted at the source. How can the source be dependent on the destination that way? How can the source symbol be in condition to the destination symbol? No, that is not the logic here. The logic is, we are finding out how x1 and y1 are related. Okay. We want the destination to get y1 when we transmit x1. That is our goal. So, we want to find out that first. That means, when I transmit x1, you should receive y1. When I transmit x2, you should receive y2. Similarly, with x3 and x4, you should receive y3 and y4. That is what is the basic requirement of the communication. If that is happening, then the communication is 100% efficient and perfect. But we know that that is not going to happen as such. We are not living in any ideal communication system as such. That is where the Bayes theorem is helping us now, where we can obtain the condition of x1 with respect to y1, which means at times, let us say, at times you have ordered for some particular item, maybe in Amazon or maybe in Swiggy or any such online portal, and you are expecting the item now. You are the destination. Amazon is the source or Swiggy is the source. Now, you can always predict the receipt of the item which you have ordered to some extent by using Bayes theorem. Depending upon the credibility of Amazon, depending upon the credibility of Swiggy, you can have a fair assumption that when will the item will arrive at your doorstep or on which day it will arrive at your doorstep. And they may also ensure that by sending you email, sending you SMS. That's all there in the field, right? Now, think in that angle, can the destination's condition be affecting the source? Or can the destination be predicting the arrival of particular symbol from the source? Now, can we model the source itself as per the requirement of the destination? Can we model Amazon itself? Can we model Swiggy itself based on our experience? Yes, we have done it, right? We have done it. We have modeled the Ola cab system. We have modeled the Uber cab system based on our requirements. Our requirements in the sense, general public requirements. That is how now even the transportation medium has become more efficient, where the people who are using the system are now characterizing the system as such based on the requirements. That is how now Amazon we know, Swiggy we know, Ola you know, Uber we know. In fact, we know even the cinemultiplexes. We can model even the malls like Mantri Mall and Orion Mall and Garuda Mall, right? Phoenix Mall. You have been doing that. Our students have been doing all these things, right? So that is what is the logic here. The logic of Bayes theorem is, you may think it is a dry mathematical formula. No, not that way. This is one of the remarkable contributions for the information theory. Always information theory and the probability and statistical findings are always hand in hand moving. Without the mathematical research, technical research is not possible. Please remember that. Only when the mathematical people find out new things, that is when those things are utilized in technology. Engineering is nothing but application of mathematics only, along with the material science. For example, all our devices are part of material science. Okay, all our signals are part of nature. But what is mathematics? Mathematics basically human ingenuity. Using their 10 fingers, people started counting from 0 till 9, and that became a decimal system. God gave us 10 fingers in 10 hands, we started using it for counting, and that is how decimal system was invented. And gradually the decimal system later on gave rise to a binary system when we had a digital logic and the invention of logic gates in electronics. Now we will have decimal to binary conversion, binary to decimal conversion, that way. Our life is utilizing decimal system, whereas machine life is utilizing binary system. Now there is a heavy usage of mathematics even in normal lifestyle. So unless there is a mathematical research, there cannot be a technical research. Okay. So that way Bayes theorem is a remarkable theorem. Bay himself, I don't know whether it is pronounced as Bay or Baye, I don't know. English is funny that way. Still, we will keep telling it as a Bayes theorem only. So this Bayes theorem is a remarkable invention in which we can find out the input conditional probability, which means we can find out the condition in which x1 is transmitted when y1 is received. That will help us in later on modeling our communication system and trying to find out the probability of error as well. We will have exercises for that. That way this will be quite interesting now. So, P of x1 slash y1, probability of x1 being transmitted when y1 is being received is equivalent to P of y1 being received when x1 is transmitted into P of x1 and divided by P of y1. Now, you can always multiply these two, right? P of x1 slash y1 into P of y1. You can equate it to P of y1 slash x1 into P of x1. You can remember the Bayes theorem that way also. The denominator here can come to the LHS now. So, we can simply write the Bayes theorem also in another form as P of x1 slash y1 into P of y1 equals P of y1 slash x1 into P of x1. So, you will have to remember the total theorem of probability and the Bayes theorem. Let me proceed now. Let us have a small exercise. I don't know whether I will be able to finish this exercise or not. It is only last 5 minutes now. But let me make an effort. I am not going to hurry up now. Whatever I can cover, I will now cover. Remaining things let me cover in the next class only. There is an exercise in a communication system. Transmitter A and receiver B are having 3 symbols each, which means we can say it is a quaternary system having the following conditional probabilities. P of B1 slash A1 equals 0.4, P of B3 slash A1 equals 0.1, P of B1 slash A2 equals 0.2, P of B2 slash A2 equals 0.6, P of B2 slash A3 equals 0.3, P of B3 slash A3 equals 0.7, P of A1 equals 0.4, P of A2 equals 0.25. Find the entropy of the transmitter and receiver. Now see, all the conditional probabilities are not given and all the input probabilities are not given. But we know the property of the channel matrix, we know the property of the source. So we can find out the missing ones. Probability of A1 is given 0.4, probability of A2 is given 0.25. Naturally, we can find out the probability of A3 is 1 minus 0.4 plus 0.25. That is 1 minus 0.65 is nothing but 0.35. Because probability of A1 plus A2 plus A3 is equal to unity. Either A1 or A2 or A3 has to be transmitted. When this is totally unity, simply put 1 minus 0.4 minus 0.25, you will get the probability of A2. In the same way, B1 slash A1 is given, B3 slash A1 is given. Let me admit the student. Okay. Due to network issues, always we will have these problems. B1 slash A1 is given, B3 slash A1 is given, B2 slash A1 is not given. You can find out B2 slash A1 just by finding out 1 minus 0.4 minus 0.1, that is 1 minus 0.5 is 0.5. Similarly, you can find out B1 slash A2 is given, B2 slash A2 is given, B3 slash A2 is not given, that is 1 minus 0.6 minus 0.2, that is 1 minus 0.8 is 0.2. Similarly, B2 slash A3 is given, B3 slash A3 is given, B1 slash A3 is not given, which means what? 1 minus 0.7 minus 0.3, that is 1 minus 1, that is 0. Look at this. That is strange, yeah? No, it is not strange. I will tell you why. Here, B2 slash A3 is given 0.3, B3 slash A3 is given is 0.7. So, 1 minus 0.7 minus 0.3, you will get probability of B1 slash A3 equal to 0. That means, the system is characterized in such a way that it will never receive B1 when A3 is transmitted. Such property is possible with the communication channels. That is how this system is modeled. So, that is also possible. So, using all this data, we can find out all the probabilities which are not given. Then, when we obtain all those probabilities, we can find the entropy of the transmitter and receiver. Let me show you that. The channel matrix, also called as noise matrix, can be written now. We have written the channel matrix. I have filled up all these things. You can see whatever is underlined is filled by me. This was not given, this was not given, this was not given. Now you know that it is 1 minus 0.4 minus 0.1, here it is 1 minus 0.2 minus 0.6, and here it is 1 minus 0.3 minus 0.7. So here it is 0.5, 0.2, 0. This is possible. Why? Probability of B1 being received when A3 being transmitted is 0 can be characterized for that particular communication system. Okay. But what cannot be 0 now? This cannot be 0. Probability B1 slash A1 cannot be 0. B2 slash A2 cannot be 0. B3 slash A3 cannot be 0. That means when you transmit A1, you should get B1 there. That probability cannot be 0. If that is 0, then there is no point in using that system at all. Please remember this. This cannot be 0, this cannot be 0, this cannot be 0. But you can see that here it is 0.4, here it is 0.6, here it is 0.7. But other things can be 0. Now let us say ideally, if this is 1, if this is 1, if this is 1, if all others are 0, then communication is 100%. I hope you understand this fact. Probability of capital B in condition with capital A is, if at all you have an identity matrix here, where the left to right diagonal is 1, 1, 1 and all other elements of this matrix are 0, then what does it mean? It means that you will receive B1 when A1 is transmitted, you will receive B2 when A2 is transmitted, and you will receive B3 when A3 is transmitted. That means the communication system is 100% efficient. There will be no errors at all. But normally that will not happen that way. That is how the system is modeled. Okay. Now based on this, P of A3 we have found out 1 minus 0.4 plus 0.5 is 0.35. Now by the theorem of total probability, we have to find out the probability of B1 now. Now using that upper theorem that is shown, probability of B1 is 0.4 into 0.4 plus 0.2 into 0.25 plus 0 into 0.35. You will just look at this noise matrix or channel matrix. Why is it called as noise matrix here? It is called as channel matrix also. Why is it called noise matrix here? Because what is noise here? From left to right, you visualize this diagonal. Except for the diagonal, all other things are noise only, no? Now B2 slash A1 is basically because of the noise only. B3 slash A1 is also because of the noise only. Similarly, B1 slash A2 and B3 slash A2. Similarly, B1 slash A3, B2 slash A3. They are all basically because of the noise only. That is why this is also called as a noise matrix. Now, by the theorem of total probability, let us find out the probability of the output symbols. That is the condition probability and in summation with the other conditional probabilities that way. So, it is 0.4 into 0.4, 0.4 into 0.4 probability of A1, then 0.2 into 0.25 probability of A2, then 0 into 0.35 that is probability of A3. That is how we get P of B1 as 0.21. Similarly, P of B2 as 0.455. And similarly, P of B3 we can directly find out by 1 minus probability of B1 and probability of B2. So that will be 0.335. Now we know the probabilities of input symbols, probabilities of output symbols. We can simply apply them in the formula and we will get H of A equals 1.59559 bits per symbol and H of B equals 1.5185 bits per symbol. You can see entropy of source is 1.559 bits per symbol, entropy of destination is 1.5185 bits per symbol. That means you can see there is a loss of information during transmission. That is because of the communication errors. Regarding this note, let me discuss only in the next class because it is slightly complicated. Now you please understand, the information content at the source is larger, information content at the destination is smaller. That means error has occurred there. Okay. Now at the destination it has to detect the errors, it has to correct the errors. That is the goal of the communication system now. Let me end today's class. Have a happy weekend. Let us meet each other or let us interact with each other once again in the next week. Take care. Bye bye.